As we look at 3.9, we've already mentioned basically what differentials are, and we've illustrated that dy is f prime of x times dx. So let's just be careful here because keep in mind that f prime is dy over dx. So if we want dy, multiply times dx, so dy is f prime times dx. That's if your function is a function of a single variable. But let's be careful. In general, you just take the derivative and then multiply it times dx. But that is for a single variable. So let's work a couple. We'll start with single variables and then we'll look at, well, what if we take the derivative of things with multiple variables? So dy, we have, let's say, sine of 3x. Then if we take the derivative of both sides, the derivative of the left is dy over dx. The derivative of this, we use the chain rules. The derivative of sine is cosine times the derivative of the inside. So dy over dx is 3 cosine of 3x. So if we want dy, multiply through by dx, dy is 3 cosine 3x dx. If you know what dx is, what x is, we can find dy. Let's do one more. We have x squared sine x. Then take the derivative of both sides with respect to x, and we get dy over dx. We have to do the product rule here, so the derivative of the first term times the second plus the first times the derivative of the second. So if we want dy, 2x sine x plus x squared cosine x dx. So in the book, there are formulas for differentials. And the main thing I want to look at is like the product rule. And what happens if we have more than one variable? For example, if I have y equals L times W, what do we get for dy? So let's suppose that we take the derivative with respect to x. So we get dy over dx on the left. We have to use a product rule here. Let's imagine L and W are both variables. So the derivative of the first term with respect to x times the second term plus the first term times the derivative of the second term with respect to x. So if we want dy, multiply both sides by dx. So dy on the left. If we multiply this term by dx, the dx goes away, and we have dl times w. If we multiply this term by dx, the dx's go away, and we have l times dw. So it's kind of is very reminiscent of the product rule for just regular derivatives. But this is in a differential form. So it's the derivative of the first variable times the second plus the differential of the second variable times the first. So after doing several of those, let's look at a word problem. Let's suppose that we want to measure the side of a square, and let's call that side x. And let's suppose that our error in measuring the side our error in measuring the side is a tenth of a centimeter, our possible error. So if I were to measure the side of that, I could get it pretty close, but I can't get it exact. So I'm going to say I can measure within 1/10 of a centimeter. And let's suppose that when we measure it, our actual square is 10 centimeters by 10 centimeters. So we want to find out, how does the error in the area relate to the error in measuring the side of that square. So as we've compared some related rates in the past, these aren't really rates. They're errors in one direction or the other, or change in one direction or the other. So area of a square is side squared. Or if you think about it as a rectangle, length times width, x times x is x squared. So if we take the derivative of both sides, dA over dx equals 2x. So the error in the area is equal to 2x times the error in the x. Now, keep in mind that when we talked about this in class, that we said that dA or dy or dv, whatever, that's approximately the change in your function. If we only have a small error or make a small change in the x direction, then those are very close. Now, if we want the exact change in the area, we would need to find the area using these dimensions and then add a 1/10 of a centimeter to each side and calculate the area, or take a 1/10 off and calculate the area. But if we're wanting to approximate the area, then this is going to be sufficient. So if I measure the side to be 10 centimeters, then the error in the area will be 2 times the measurement I get times my possible error. So the error in area, 2 times 10, that's 20. 20 times a 1/10 is 2, and that'll be centimeters squared. So if I'm off by a 1/10 of a centimeter when I measure the side of this square, then I could be off by 2 square centimeters when in my error or my area calculation. Now on this one, let's compare that to the actual error. So we said A equals x squared. So if I measure it to be 10, then if it is exactly 10, that gives us 100 centimeters squared. But if it's actually 10.1, let's see, 0.1 squared, then 102.01 is the actual area. Or if I'm a 1/10 less than 10, so 9.9, then the area is actually 98.01. So notice this is the area for exactly 10 centimeters. If I'm a 1/10 above, I calculate 2.01 centimeters squared too much. If I'm a 1/10 below, then I'm 1.99 centimeters squared below the actual area. So basically, I'm within 2 square centimeters of the desired amount if I measure within 1/10 of a centimeter. All right, let's do another. Let's suppose I have a circle. And let's suppose that I'm measuring the radius of this circle, which generally that's a little harder to do than measuring the diameter. But let's suppose that I measure the radius to be 4 inches. But I could have some error in that measurement. I could have the 32nd of an inch in my radius measurement of error. So let's see how much error that's going to give us when we calculate the area. Basically, if it's not exactly 4 inches, if it's within a 32nd of an inch, how much variation can we have in our area? We can figure out exactly what our area would be if that's the exact radius. But when we measure things, we may not get exactly the correct answer. So if we're within this tolerance, then how much tolerance does that give us in the area? So the area of a circle is pi r squared. So if I want the differential dA, our variable is r, so let's take the derivative with respect to r. So dA over dr, pi is a constant. When I take the derivative of this with respect to r, bring down the 2, r to the 1 less power. So dA is 2 pi r dr. So this tells us how the error in the area is related to the error in the radius. So if I measure the radius to be 4 inches, and there's a possibility of being 1/32nd of an inch off in that measurement, then my area could have an error of 2 times 4, so 8 pi over 32, or pi over 4. If r was in inches, this area dA would be in square inches, which pi over 4, 0.78, or 0.79 square inches. So if I have the potential of having an error in measuring the radius of a 32nd of an inch, then I'll be potentially off in my calculation by 0.8 of a square inch when calculating the area. Which is important to know because some things we can't measure. Some things have to be calculated. Generally, for example, if I want velocity, that's a distance divided by time. I can't necessarily measure velocity, but that's something I can calculate. I can calculate a distance different ways. I can calculate a time with a stopwatch, but each of those have the potential of having error in it. So if I want to know, well, if I calculate such and such for the distance and such for the time, but I know my distance can have a certain error in it and my time can have a certain error in it, how does that translate to an error in velocity? If I calculate my actual velocity to be a certain number, but I know these could have a little bit of error in them, how far off does that make my velocity calculation? So I guess we can do that real quickly. So if velocity is distance divided by time, if we look at the rules for calculating differentials of a quotient, we could use the formula. dv is the error in the numerator times the denominator minus the numerator times the error in the denominator over the denominator squared. If you think about taking the derivative of that with respect to x, dv over dx is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. But to get dv, if we multiply both sides by dx, these will cancel if we multiply this side by dx. The dx's on top will cancel. So dd times t minus d times dt over t squared. So if I have a distance of 15 feet with a possible error of 0.5 feet, and I have a time of 4 seconds with a possible error in that of 1/10 of a second, then we can figure out, well, okay, our velocity that we calculate is 15 feet per 4 seconds. 15 divided by 4 is 3.75 feet per second. But again, since we were taking measurements and using those to do that calculation, it might not be exactly 3.75. So we have the potential error in velocity of dd 0.5 times t, 4, minus the distance, 5, or 15, times dt, 0.1, over time, 4 squared. So 0.5 times 4, what's that, 2, minus 1.5 over 16. So 0.5 over 16, 0.031 feet per second. So the actual velocity that we calculated was 3.75 feet per second, but we could be off by a little bit. We could be off by as much as 3/100ths of a foot per second too much, or 3/100ths of a foot per second too little. So that's roughly what our error would be under those restrictions. So let's look at a problem out of the book. Let's see. Let's look at number 30. It tells us that the radius of a spherical balloon is measured to be 8 inches with a possible error of 0.02 inches. And we'll do part A. Part A says use differentials to approximate the error in computing the volume. So basically, what is the error in the volume? So volume of a sphere is 4/3 times pi r cubed. So if we take the derivative of both sides, since our variable is r, we can take the derivative with respect to something else, but let's just take it with respect to r. So the derivative with respect to r is dv over dr. On the right side, bring the 3 down. The 3 on bottom, the 3 on top would cancel, leaving us 4 pi r to the 1 less power. So dv is 4 pi r squared dr. So that's how the error in volume relates to the error in radius. So dv is 4 pi. The radius is measured to be 8. That gets squared times 0.02. So 4 times 64 times 0.02. 5.12, did I do that correctly? 4 times 64 times 0.02. So 5.12 pi, which is roughly 10 or 16.08. The radius is in inches. This is a volume, so this would be in cubic inches. So then part C asked to approximate the percent error in measuring the volume. So percent error, basically the error is what percent of the actual volume. So when we look for percent error, we take the part, how much are we off, divided by the whole. So let's do this in terms of our variables. So dv is 4 pi r squared dr. Volume 4/3 pi r cubed. So this is percent error in volume. So the error in volume divided by the actual volume. Notice some things cancel. Pi on top, pi on bottom, cancel. R squared, R cubed reduce. If we have a 4 on top, dividing by 4/3 is like multiplying by the reciprocal. So that reduces to a 3 on top. So that leaves us 3 dr on top, r on bottom. So the percent error in volume, dv over v, is equal to 3 dr over r. Now, keep in mind, this is the part of the radius, the error in radius over radius. This is actually percent error of the radius. This is a percent error of the volume. So the percent error of volume is 3 times dr 0.02 over the radius, 8. 3 times 0.02 divided by 8. So 0.0075. And notice that doesn't have any units. That's a decimal. or as a percent, 0.75%. So the error that we get when we calculate the volume, that's less than 1% of the actual volume. So percent error in volume, that's compared to the whole volume, how much is my error? Well, the area is less than 1%. It's 0.75%. So occasionally you'll be given a problem and you'll be asked, if I want to be within this certain percent error, then how accurate do I need to make a certain measurement? All right, let's consider this example. Let's suppose that we're producing mufflers at some company. And when we produce these mufflers, we can only, for airflow rate reasons and so forth, we can only have an error of 2% in our error calculation. So 2% error in area. And let's find out how accurate does the radius need to be measured. Another way of thinking about it, what is the allowable error in production of the radius? So you're looking at an assembly line, and you know that coming off that assembly line, we know what the desired area is, and I'll give you that number in a minute. But we can be within 2% of that particular area, and this be a sufficient part. But if we get beyond that value, then we have to discard the part and not use it. So how much tolerance is allowed in our radius so that we get this maximum error in our area? So how accurate does our radius need to be measured? And let's say if area needs to be 4 pi. And actually, let's make up a different number. Let's say 16 square inches. So how accurate does the radius need to be measured if the area needs to be 16 square inches? So if we're looking at a circle, then of course the area is pi r squared. So let's begin by comparing the error in the area to the error in the radius. So dA over dr is 2 pi r. Pi is a constant, bring the 2 down, r to the 1 less power. So dA is 2 pi r dr. So we're told that dA over A, which is percent error in area, needs to be smaller than 3%, so less than or equal to 3%. So dA over A needs to be less than or equal to 0.03. Now dA is 2 pi r dr. A was pi, r squared. So that needs to be less than or equal to 0.03. So the 2's cancel, the r's reduce, so we come out with 2 dr over r. So one thing we could figure out at this point is how the error, the percent error in the area compares to the percent error in radius. Basically, if we were to divide by 2, the percent error in area would be, or the percent error in radius would have to be half the percent error in the area. But if we're wanting to find the allowable tolerance or error in measuring the radius, to get rid of this r, multiply both sides by r. To get dr by itself, divide both sides by 2. So the maximum allowable error in the radius for producing these mufflers will be 0.03 times the radius divided by 2. Now we need to keep in mind, well, what does our radius need to be? So we're told our area needs to be preferably exactly 16 square inches. And recall that area is pi r squared. So if we know the desired area, then we can figure out what the exact radius should be. And then we can figure out, well, what is our allowable tolerance in measuring the radius or in producing the muffler with that radius. So to get r by itself, divide by pi. To get r, take the square root of both sides. So if we take 16 divided by pi, then take the square root, we get, and since we're going to a percent of 0.03, I'm just going to keep a bunch of decimals for now. Let's say 2.25676. 2.25676. And if area was in square inches, that would be in inches. So our radius needs to be measured within 0.03 times 2.25676 divided by 2. So the radius needs to be measured within, let's see, 0.03 times 2.25676 divided by 2, 0.03385 inches. So that's how much error in the radius is allowed if our area and error in the area has to be no more than 3%. So if that means our radius, if our area has to be 16 square inches, that means our radius has to be this, and we can't be off by farther than this.